Hi everybody, I'm Yuri Gardinazzi, a second-year PhD student at the University of Trieste, and I'm doing my PhD in collaboration with the Research Institute Area Science Park. Today, I'll show you how we worked with ZigZag persistence and the statistics that we used to interpret a high nonlinear system with point clouds that move in a high-dimensional space. ZigZag is an algorithm that allows us to study the evolution of topological features of a point cloud that evolves. To do that, we need to do a simplicial complex over each time step, and then we can decide if we want to use unions or intersection between these cloud points. For our use case, we used intersections. And now you can track the connected components that, as you can see, at the time step 2, one more connected component arise, and you can see that the loop is destroyed at the time step 2. But the standard algorithm for ZigZag wasn't enough for us, so we had to use fast ZigZag. There is the code available on GitHub, and fast ZigZag allowed us to study the evolution of a cloud point of around 10,000 points that wasn't feasible with the standard algorithms. I also highly suggest the talk of Tamal Day on fast ZigZag if you want to know more about it. Our case, that as I said is high dimensional, is the study of the inner workings of large language models. These models are deep learning models trained to do next token prediction. So given a prompt, given a sentence, they predict the next word. To do that, they tokenize the sentence in tokens, and each token is then sent to this embedding space that is a high dimensional space. And these models are relatively simple because they are essentially built with these transformer layers that are repeated n time. So since the model is trained to do next token prediction, we use the last token as a way to represent a sentence. And this methodology is done in many different works in the literature. Because while the model reads each token, where it sends in this high dimensional space the next token, it changes position depending on what the model read before. So for each token, we have this vector on around 1000 dimensions for the work I will show you that we will call internal representation. So in our case, the zigzags changes in the following way, where we have a cloud point that instead of time travels through different layers. And then we have the intersection layers. Since the model does a lot of nonlinear transformation from layer I and layer I plus 1, we decided to build our simplicial complex with a K-NN graph, because the choice of a radius for vector strip wasn't trivial in our case. So in this example, we connect points with the two closest nearest neighbors, and then we build the simplices when we have 3 adjacent edges. So this way of building a simplicial complex is really useful if you're working with points in really high dimensions. And you find absolutely not trivial to find a radius, for example, for vector strips. Then why this methodology? Because we want to study how model rearranges different sentences, let's say, across time as it processes them. And also, we wanted to see if we could confirm certain results that were present in literature, for example, with more geometrical analysis. And this framework allows us also to study a model as a whole, while in a lot of works, what is done is to compare layers independently pairwise, or just look at single layers one by one, while ZigZag allows us to see the entire evolution of the information through the model. We have intersection layers, but intuitively the model has just the normal layers, so we sum the features that are burned and destroyed in the intersection to normal layers that from ZigZag will have even indexes. Then we used what we call birth relative frequencies. That is a statistics that tells us the rate at which new high-dimensional holes are created through the model. And we use the parameter alpha to weight the features that are short-lived with negative values of alpha, or to weight more features that live more through the model that persist more with positive values of alpha. We also did what we call the interlayer persistence. That is a statistics that tells us the probability that a cycle alive, a loop alive at a given layer is present elsewhere, before or after. And then we power weight these measures with the same parameter alpha that I showed you before. So what we get as a result is this persistence diagram, where we have on the x-axis the layer where features are created, and on the y-axis how long they persist through the model. And then we can already see by eye that at the beginning of the model there aren't a lot of features that persist. They don't persist at all until the end. While the more we go deeper in the model, we find more and more features that persist more. But this diagram is not immediate to look at, to analyze. So with the birth relative frequencies and alpha equal to -1, we give weight to features that are short-lived. You can already see from this plot that there is a bump at the very beginning where a lot of features, where a lot of short-lived features are being created. Then with alpha equal to 2, we see that in the middle of the model that is not clear by eye, a lot of features that persist more are created. Then with the interlayer persistence, we can see that the model is creating more and more features that persist more. And this is consistent with different values of alpha. And then these features reaches a plateau in this stage of the model, meaning that points are not rearranging that much. Because if a feature persists, it means that the cycle is not destroyed. So, and we also see that towards the end, the points are moving more and more towards the output. And during this phase, features do not persist anymore. Do not persist that much anymore. We see that this result is consistent also with different transformer models that have the same amount of layers and the same hidden dimension. And also these models have the same amount of parameters, a comparable amount of parameters. We also saw that this statistics is, this dynamics is consistent also with different datasets. Code is a dataset of programming code from GitHub, SST movie reviews, math is a dataset of mathematical problems, and Pile is a more general dataset with more or less everything inside it. Then we said, okay, we are saying that at the beginning more and more features are being created. These features reach a plateau, meaning that points are not rearranging that much. And then there's a phase, a decreasing phase, where points are rearranging more and more towards the output and features are being destroyed. We decided to test this theory with different benchmark. In this case, I show you MMLU, that is a multiple choice benchmark. And we see that if we cut the layers at the beginning in a block of 5 layers, These layers are really important for the model. So we get performances close to random choice, essentially. While if we cut layers where points are not rearranging that much, the performances degrade, but the model is still usable. They degrade, but not that much. While if we cut layers towards the end of the model, performances drop by a lot. So these layers, this decreasing phase is really important for the model. So these are the result on the interpretability side of large language models that we were able to do with ZigZag persistence. I hope you found these statistics useful and maybe you can use them in your work. You can find our work that is at the moment on archive and also the ZigZag papers. And attention is all you need is the historical paper of transformers, while here you have the past ZigZag repo and our repository on the way we apply ZigZag on LLMs. Thank you for your attention.